Stars are the building blocks of galaxies. They illuminate the cosmos and provide the energy for life. Their births, lives, and deaths drive the evolution of the universe. Understanding stars is key to understanding our place in the grand scheme of things. Stars form in vast clouds of gas and dust called nebulae. These nebulae are cold and dark, rich in hydrogen and helium, the primary ingredients of stars. Gravity is the driving force behind star formation. It pulls the gas and dust together, causing the nebula to collapse in on itself. As the nebula collapses, it fragments into smaller, denser clumps. These clumps continue to contract under their own gravity, their temperatures and pressures rising steadily. This process can take millions of years. Eventually, the core of a collapsing clump reaches a critical temperature and pressure. At this point, nuclear fusion ignites and a star is born. The newly formed star blasts away the remaining gas and dust, announcing its arrival to the cosmos. Before a star reaches the main sequence, it exists as a protostar. This phase is characterized by intense heat and luminosity, powered by infalling matter. Protostars are often obscured by their birth cloud, making them difficult to observe. As a protostar accretes material, its core temperature and pressure increase. This leads to more efficient nuclear fusion reactions. The protostar's luminosity increases, pushing back against the infalling material. This creates a stellar wind, carving out cavities in the surrounding gas and dust. The young star gradually reveals itself. The main sequence is the longest and most stable period in a star's life. During this phase, stars fuse hydrogen into helium in their cores, generating the energy that makes them shine. The Sun, our own star, is currently about halfway through its main sequence lifetime, which is estimated to last around 10 billion years. Stars on the main sequence exhibit a wide range of characteristics, including size, temperature, and luminosity. These properties are primarily determined by the star's mass. More massive stars are hotter, brighter, and have shorter lifespans than their less massive counterparts. Astronomers classify main sequence stars using a system based on their spectral type, which is determined by their temperature and color. The spectral classes from hottest to coolest are O, B, A, F, G, K, and M. O-type stars are the hottest and most massive, emitting intense blue-white light. M-type stars, like our Sun, are cooler and less massive, emitting yellow or red light. The spectral type of a star provides valuable insights into its properties and evolutionary stage. Red dwarfs are the smallest and coolest type of main sequence star. They are significantly less massive than our Sun and emit a faint red light. Despite their diminutive size, red dwarfs are incredibly long-lived, with lifespans exceeding trillions of years. The longevity of red dwarfs stems from their slow and efficient fusion rates. They consume their hydrogen fuel at a leisurely pace, ensuring a long and stable existence. In fact, the universe is not old enough for any red dwarf to have reached the end of its main sequence lifetime. Due to their low luminosity, red dwarfs are difficult to observe individually. However, they are incredibly common, comprising the vast majority of stars in the Milky Way galaxy. Their sheer numbers make them important contributors to the overall stellar population. While red dwarfs are too faint to be seen with the naked eye from Earth, they are of great interest to astronomers. Their long lifespans and potential for hosting habitable planets make them prime targets in the search for extraterrestrial life. As stars exhaust the hydrogen fuel in their cores, they leave the main sequence and enter the next stage of their evolution. For stars similar in mass to our Sun, this involves expanding into red giants. Red giants are much larger and cooler than their main sequence counterparts, with cooler surface temperatures but significantly higher luminosities. The expansion into a red giant occurs because the star's core contracts and heats up, igniting hydrogen fusion in a shell surrounding the core. This increased energy output pushes the outer layers of the star outward, causing it to swell in size. More massive stars evolve differently, becoming blue giants instead of red giants. Blue giants are extremely hot and luminous, with short but brilliant lives. They fuse helium and heavier elements in their cores, producing enormous amounts of energy. Both red and blue giants represent a transitional phase in a star's life. They are relatively short-lived compared to the main sequence, eventually exhausting their nuclear fuel and evolving into stellar remnants. Supergiants are the largest and most luminous stars in the universe. They are even more massive and luminous than giants, with short lifespans measured in millions of years. Supergiants represent the final stages of evolution for the most massive stars. Betelgeuse and Rigel, two of the brightest stars in the night sky, are prime examples of supergiants. Betelgeuse, a red supergiant in the constellation Orion, is nearing the end of its life and is expected to explode as a supernova in the astronomically near future. Rigel, a blue supergiant in the same constellation, is much hotter and more massive than Betelgeuse. It is still fusing heavier elements in its core, but it will eventually meet a similar fate, albeit on a much shorter timescale. Supergiants are cosmic powerhouses, emitting vast amounts of energy and enriching the interstellar medium with heavy elements through their stellar winds and eventual supernova explosions. Their brief but brilliant lives play a crucial role in the evolution of galaxies. When a star like our Sun exhausts its nuclear fuel, it sheds its outer layers, leaving behind a dense, Earth-sized core known as a white dwarf. White dwarfs are incredibly hot when they first form, with surface temperatures exceeding 100,000 degrees Celsius. However, white dwarfs no longer generate energy through nuclear fusion. Instead, they slowly cool over billions of years, radiating away their residual heat. As they cool, their luminosity decreases and they gradually fade from view. Despite their small size, white dwarfs are incredibly dense, with masses comparable to that of the Sun, packed into a volume the size of Earth. A teaspoonful of white dwarf material would weigh several tons on Earth. White dwarfs represent the final evolutionary stage for most stars in the Milky Way, including our own Sun. Their cooling process provides a glimpse into the distant future of our solar system. Section 8. Neutron stars, Pulsars, and the densest objects in the universe. Neutron stars are the remnants of massive stars that have exploded as supernovae. They are even denser than white dwarfs, with masses greater than the Sun squeezed into a sphere only a few miles across. A teaspoonful of neutron star material would weigh billions of tons on Earth. Neutron stars are composed almost entirely of neutrons, subatomic particles with no electrical charge. The immense pressure within a neutron star forces electrons and protons to combine, forming neutrons. Some neutron stars, known as pulsars, emit beams of radiation that sweep across space like cosmic lighthouses. These beams are produced by the star's rapid rotation and its intense magnetic field. Neutron stars are fascinating objects that push the limits of our understanding of physics. Their extreme density and gravity create conditions unlike anything found on Earth, providing insights into the nature of matter under extreme conditions. Section 9. Black holes, where gravity reigns supreme. Black holes are the most extreme objects in the universe, where gravity is so strong that nothing, not even light, can escape. They form when massive stars collapse, creating regions where the laws of physics break down. The boundary of a black hole is called the event horizon, a point of no return. Anything crossing the event horizon is drawn inward to the singularity. Their presence is inferred by gravitational effects on surrounding matter. Black holes continue to fascinate and challenge our understanding of the universe. Section 10. Stellar exotica, variable stars, brown dwarfs, and hypergiants. The universe is filled with a diverse array of stars, each with its own unique properties. Variable stars exhibit variations in their brightness over time. Brown dwarfs are not massive enough to sustain nuclear fusion in their cores. Hypergiants are the most massive and luminous stars known. These unusual star types provide valuable insights into stellar evolution and the extremes of physics. Section 11. The circle of stellar life and death. Stars are not static objects but rather dynamic entities that undergo a continuous cycle of birth, life, and death. This cycle, known as stellar evolution, is driven by the interplay between gravity and nuclear fusion. Stars form in vast clouds of gas and dust, ignited by the force of gravity. They spend the majority of their lives on the main sequence, fusing hydrogen into helium in their cores. As they exhaust their fuel, they evolve into giants or supergiants, eventually shedding their outer layers or exploding as supernovae. The remnants of stellar evolution such as white dwarfs, neutron stars, and black holes continue to influence their surroundings, shaping the interstellar medium and influencing the formation of new stars. The life cycle of stars is a fundamental process in the universe, responsible for creating the elements that make up planets, life, and everything we see around us. Understanding stellar evolution is crucial to understanding our place in the cosmos.